So this is a quick rundown of the UF MathGeo model developed by myself, Dr. Maya Marticheva at the UF Department of Mathematics, and Dr. Sadie Ryan in the Geography Department. Our model consists of two compartments. The first represents non-adults, which includes egg, larval, and pupal stages. The second compartment represents the adult stage. The number of non-adults is determined by egg production, um, the environment's capacity to support non-adults, and also you have removal from deaths and maturations onto the adult stage. The number of adults is determined by the number of maturations, and you have removal from deaths. The red bits are temperature dependent, while the blue bits are precipitation dependent. This is the full representation of the model. So a part like egg production, that's a result of the number of adults you have multiplied by their fecundity and multiplied by the number of blood meals they take. Um, and again, so these the red parts are all life history traits, and these are dependent on temperature. These are those traits in the previous slide. Um, they were taken from a paper by Aaron Mordecai and others where they compiled 12 or 13 laboratory studies where mosquitoes were put in different temperature treatments. So, for example, biting rate doesn't indefinitely go up with temperature. It's a nonlinear function. There's an optimal temperature for performance. So that's the case with all of these traits. The data we use in our process include the traits on the previous slide, the mosquito data that was provided, a shapefile from the U.S. Census Bureau of the counties, which we use to extract climate data. Our climate data is it comes from the PRISM climate data set compiled at Oregon State University and the NOAA climate forecasts for next month and next season. On the left is an example of a layer from the PRISM data set. This comes directly off their website. On the right is an example of a NOAA climate forecast. They give the probability of the temperature or precipitation falling above, at, or below a historical normal, and these have to be converted in order to be used in our model. So the first step in our process is to model the historical population of Aedes albopictus and Aedes aegypti in all of our counties. And this runs from 2007 to 2018. So we fit those curves to the traits I showed you earlier, and then we extract climate data for each county. We run our model, and then we fit a detection curve, and I'll go into detail in a bit. So this is what the output looks like for a given county and a given species. You can see the number of adults and the number of non-adults changes with varying temperature and precipitation. So next what we do is we look at the simulated number of adults in a given county, and we compare that to the historical record. So if the species was detected for a given month, that's a 1, and if it was not detected, that's a 0. And we fit a logarithmic function, so we can convert the predicted population from the model into a probability of detection. The second step in our process is to model the current population of Aedes albopictus and Aedes aegypti in all of the counties. So what we do is we'll compile the 2019 climate data from the PRISM dataset, and then we'll use the NOAA forecast to look into the next month. We'll extract that data to each county, and then we will run a model for 2019, picking up where the historical model left off. And then using the result of that model, we can estimate presence using that detection curve I just showed you. This is the entire process. I'd be happy to go over this with anyone interested. These are some of our predictions from April, as an example for Aedes aegypti, and these are some of our predictions for Aedes albopictus.